In 2.1, we're going to look at basic differentiation rules and rates of change. What we saw in the previous section is we can take our idea of the slope of a tangent line and we can take the limit of it, and we did quite a few examples, and it was such a long limit process. Surely, doing the same process over and over and over, we can find some shortcuts to help us with that. And that's what you're going to see here, is you're going to see our basic rules that we're going to use to shortcut that whole limit process, because trends and patterns began to occur as you saw in those examples. So we're going to start with kind of from the bottom and work our way up into harder examples. So the first thing you're going to learn is the constant rule. The constant rule says this: if I am taking the derivative of some, just say c value, then the derivative of it will always be 0. So say I had f of x equal to 7, then its derivative, so I would say f prime of x, would be equal to 0. And let's see why this would make sense. If I were to take f of x equal to 7, that's like y equal to 7, that's just a horizontal line. You can see that the slope at any given point on that line is equal to 0. So if we were taking any given function f of x, c, then f prime of it will be 0, because these are just all horizontal lines, so the derivative at any point on a horizontal line would just be 0. So s of t equal to -3, that means s prime of t would be 0. Say y was equal to 1 million, then y prime would still be equal to 0. So we can kind of just make a statement here. If it's a constant, just a number, no variable, the slope or calculus derivative is 0. And you can see we have that written here. Okay, so pretty basic, just numbers, derivative 0. So let's go into the power rule. The power rule is one that we are going to use probably the most of all your rules, and we're also going to build upon it into some other sections. It says if n is a rational number. Now remember, rational numbers are anything that can be written as a fraction, and the function f of x is equal to x to the n is differentiable, then we know that f prime of x is equal to nx n to the -1. And so let me write that a little bit bigger for you so you can kind of see that exponent a little bit larger. If f of x is equal to x to the n power, then what you're going to do in order to create f prime of x is you are going to take this exponent here and you're going to move it out front. You're going to leave that x alone, and you're going to subtract 1 from the exponent. And so again, I just want to write it larger for you there so you could see the smaller exponents and then the larger coefficients out front. And so this is true for any n that's a rational number. So positives or negatives or fractions, this is going to work for us. Bring the exponent down and subtract 1. So let's see it a little bit more clearly with some numbers. And so you can see here, f of x is equal to x cubed. And so then that means that f prime of x would be equal to, so I'm going to take this exponent right here and I'm going to move it out front so it becomes a large 3 out front of that x. And then you're going to do 3 minus 1. Clean that up. That gives me 3x squared. Now you can see I did equal signs here in between because these are my derivatives, but I didn't do f of x is equal to this because f of x and f prime are not equal. Now, as I work some of these early examples, you're going to see me do things like this. You're going to see me write 3 minus 1, but you are an educated individual. I do not expect you, especially in an exam situation, to write 3 minus 1. But I don't know when you're watching this or when you're working through this, so I didn't want to just write 3x squared and you just wonder where the 2 came from. So I'm just trying to show you the process of how those numbers are appearing. But no, as you work with these and move forward and get to an exam situation, those shortcuts I assume you are going to take. So let's look at the next one. The next one says f of x is equal to 2x to the 4th. So I'm going to come over here to the side. I'm going to say f prime of x is equal to, I'm going to take this exponent and I'm going to bring it out front. Now I already have a 2x in this problem. So when I bring that 4 out front, I'm going to have to multiply it by the 2 that's already there. And then that 4, again, for notes purposes, I'm going to say 4 minus 1. So then I'm going to clean this up. So that gives me 8x to the third power. And that would be my derivative. And again, the more you work with this, the more you're going to see how you're going to be kind of doing these mentally in your head and working through these. So let's move on to some other examples, still working with this power rule. Again, I want to find the derivative. So number 3 says f of x is equal to 2x to the first power. All right, so I'm going to find f prime of x. I'm going to say f prime of x is equal to, I'm going to bring that exponent out front. So it gives me 1 times 2, x to the 1 minus 1. Clean that up. That's just 2x to the 0 power. Now remember from algebra 1, anything to the 0 power is just 1. Anything to 0 power is just 1. So I further need to clean this up because this would be equal to 2 times 1. So it would just give me a value of 2. Well, that kind of makes sense. If you saw from earlier lectures, whenever if we have f of x equal to 2x, that's a linear function. It has a slope of 2. The slope is 2 the entire way of the function. So it makes sense that I would just get a value of positive 2 here. Look at this next one. Sometimes when you're working through derivatives, you need to do your algebra first and then your calculus. In this previous example, I worked through it and I did my calculus first, and then this part down here was just my algebra. Well, in this next example, I'm going to do some algebra first to rewrite it, and then I'm going to apply my calculus. So again, going back to algebra 1, if you remember, we can rewrite a radical as a rational exponent. The number in the bottom is the root. The number in the top is the power that was on the x. Now that I have g of x equal to x to the 1/3 power, I can now take the derivative. So I'm going to say g prime of x is equal to, I'm going to bring the 1/3 down, and I'm going to subtract 1 from it. Now, when I subtract 1 from it, when you're working with the power rule, negatives and fractions are going to be the things that kind of trip you up. And I'm going to show you the negative here in a minute. So with a fraction, be careful with this. Use your handy dandy calculator if you need to as you go. So this means this would be equal to 1/3 x to the, now remember, 1/3 minus 1, if I get a common denominator, would be 3 minus 3. So that would be 1/3 x to the negative 2/3. And again, back to our algebra, you can't ever leave a negative exponent. So you got to do some cleanup. Not done yet. And so then this would mean that g prime of x is equal to, now remember, if you have a negative exponent, say I had, switch back to the color I was using up here. Whenever you have a negative exponent, you're going to move it in order to create a positive exponent. So I would take this and move it to the bottom. Now I always say move it because if you have anything else within the problem, it would need to stay where it is. So back to our original problem down here, I'm going to now take this x to the negative 2/3. I'm going to place it in the denominator. So it gives me 1/3 that was already down there, and then an x to the positive 2/3. So moving it to the denominator gives me a positive exponent. And then my rule of thumb is always put your problem back in the order, in the format that it was given to you. Since we were given a cube root, I'm going to change this back to a root. So this gives me 1/3, the cube root of x squared. And that would be my final answer. Now you'll notice with this, when I was working with this, I had to do some algebra. And then I did the calculus. And then I did some algebra. And so make sure you're remembering all that you learned from your algebra and pre-cal days, because that's what's going to aid you in either getting something into a form that you can work with, or it's going to aid you and cleaning up a problem that you're working with. So those algebra skills are really honing in on, really pulling in as we work through some new calculus concepts. So I told you the two things that are going to trip you up when you're working your power rule are going to be your negatives and your square roots. And so here's an example of one here. So with this one again, I only know that if I have a function raised to the nth power, that its derivative would be bring the exponent down and subtract 1 from it. But my current problem doesn't look like that. So the first thing I have to do is some algebra and convert it into that form. So this would be equal to the reverse of the previous problem. If I take what is in the denominator, or just this variable of an x squared, and move it to the top, this becomes x to the negative 2. Although it is not a preferred format for completing a problem, it is the preferred format for us to actually execute the calculus in this. So then that means my derivative would be equal to bring the exponent down and then subtract 1 from it. So again, fractions and negatives are normally where students have a problem. And so you say, well, then that is equal to negative 2x to the negative 3. And that would be my derivative. Now, that's not very good format. So again, you can't, kind of re-emphasize here, you can't leave a negative exponent. So take it one step further, and we're going to take this x to the negative 3 and put it back in our denominator. So that gives me negative 2 to the x minus 3, x to the third. And then I'm done with that problem. So power rule is going to be really handy for you. It's going to help you to find these derivatives or our slopes of our tangent lines at any point. But just make sure that you are doing your algebra correctly, you're moving things around correctly, and that you're finishing up your simplification. So these were kind of some basic problems. Let's go into some examples that have a little bit more words to them. This one says, find the slope of a graph f of x equal to x to the fourth when x is negative 1, when x is 0, and when x is 1. Just kind of fix that right there. When x is equal to negative 1. Now, in order for me to find a slope at an individual point, you want to be thinking derivative. So when you saw this word and you saw that it said slope, in your mind, I want you to think slope, derivative. And so we're going to take our function, and I'm going to say f of x is equal to x to the fourth. So I'm going to find my derivative, f prime of x is equal to bring the exponent down. So 4x to the subtract 1 from it, 3. So there's that shortcut I'm showing you of I'm not going to write down 4 minus 1 a lot. So now I have my derivative. Now the next part says when x is negative 1, x is 0, and x is 1. So now I just have to plug into that. And so what I'm going to do is I'm going to say f prime of negative 1, keeping my notation, so that would be 4 times negative 1 cubed. So that gives me a negative 4. Be careful with your negatives. Use your calculator to help you with that. So f prime of 0 is equal to 4 times 0 cubed. So that gives me 0. And then f prime of 1 is equal to 4 times 1 cubed. So just positive 4. Aren't you glad we learned the shortcut in 2.1 so that we didn't have to work through that long limit process as you saw in the previous section? Now, additionally, it says this. It says, what is, thought I had it on the next screen here. Additionally, if I want to take this a step further, and I want to say, what is the equation of the tangent line at x equal to negative 1 and use y minus y1 equal to m of x minus x1. So pulling up some more algebra skills. So if I want to know what the equation of a tangent line is at x equal to negative 1, I'm going to have to know a little bit of information. I'm going to have to know a slope, and I'm going to have to know a point. And if I have those pieces of information, I can find the equation of a line. Well, I see that I have an x value. I know that the slope at -1 is -4. We just found that in the first part. So the only thing that we are lacking is this y1. Now, when you're looking back at this problem and you're working with this, the derivative is going to give you the slope. The function itself is going to be where you find its placement, or you're going to be using that to find any missing y values, because that's going to tell you the placement of it, but plugging into the derivative is telling you the slope. So in this problem, I've got m equal to -4. I've got my x1 equal to -1, but I have to plug in that x1 into the original, which was x to the 4th, in order to get that y value. So -1 to the 4th power just gives me +1. And so now I have my y1. So I can now work it from over here. So I'm going to say y minus 1 is equal to m -4, x minus -1. Be careful with those negatives. So you've got to remember how to find equations of line like we did in algebra and in pre-calc. Now clean this up. This gives me y minus 1 is equal to distribute. Now negative and negative, that makes a positive. So I end up with -4x minus 4. So I'm going to add 1 to both sides. I get y equal to -4x. See, -4 plus 1 is -3. And I now have an equation of a line at x equals -1. And that equation is y equals -4x minus 3. So we just found the tangent line. Kind of one of those concepts we've been talking about here for a little bit. So you can see this idea of derivative and creating these shortcuts with our constant rule and with our power rule are really handy to us, so that we're not working through that long limit process, and we can now get to these that we are working with and taking it up a notch. Like, okay, let's find that equation of the tangent line that we've been talking about so much. So let's continue this path and talk about some rules. Now the next rule we're going to look at is, again, looking at that constant rule. And it says that if I am taking the derivative with respect to x of c of f of x, that would be equal to c times f prime. Basically what this is telling you, and again, there's that different notation for derivative, is if you have some kind of constant right here on your function, that it's just going to go along for the ride when you move into your derivative. And we really kind of saw this already in a previous example when we brought that 4 down and multiplied it by that 2. You notice that 2 just went along for the ride. And so again, let's just kind of make some notes on this. Remember, this notation here just means take the derivative. So it's like your instructions. So pretty brief. You got to know what those mean. And then this c right here, that's just your constant. And so it's going to go along for the ride as you're working through on your derivatives. So let's look at that kind of with some numbers to make a little bit more sense for you. And so when we're working on this first one here, f of x is equal to 3x squared, and we want to find the derivative. So I'm going to say f prime of x is equal to 3 is just going to go along for the ride. And then I'm going to work with this x squared. So I'm going to bring the exponent down, subtract 1 from it, if you like. All right, 2 minus 1. And then I'm going to clean that up. So 3 times 2 gives me a 6. X to the 2 minus 1, which is 1. So 6x would be my final answer. And so again, I'm just trying to show you that this constant 3 just went along for the ride as you took the derivative of the function itself, x squared. Let's do the same thing again in this next one. And so I'm going to say, first, let's do some algebra. So this would be the same thing as, let's bring this up like a previous example, and that would be 2x to the -1. If there's not an exponent, there's an assumed 1 right there, and we move it to the top, when you move it to the top, that gives you a -1. And so now that I have it in this better form of power rule, I can take the derivative. So I get y prime is equal to 2 is going to go along for the ride. I'm going to bring the -1 down, and I'm going to subtract 1 from it. Be careful with those negatives. So if I multiply these two together, I get -2. And if I subtract that 1, that gives me a -2 as well. Then clean it up. Yes, we converted it in order to apply our power rule, but you always want to clean up your problem and simplify it as much as you can, following all your math rules. And so then this would give me -2 over x squared. Okay, let's look at this next one. This next one looks real similar to number 2, but actually I want to kind of play with some of these pieces. So when you're working with this problem here, this is actually the same thing as f of t equal to 4 over 5 t squared. Whether you have the t squared in the numerator or if you have it out to the side, those are the same. So in this case, again, this 4/5 is my constant, and it's going to go along for the ride. And so I would say f prime of t is equal to 4/5 is just going to stay out front. Then I'm going to say times, bring the 2 down, subtract 1 from it. So cleaning that up, that gives me 4/5 times 2t to the first. And then let me multiply that 2 in there. Remember, multiplying fractions, you could just put that over 1. So it tells me f prime of t is equal to 8 over 5t. And that would be my derivative. And again, having that t out to the side or having that t in the numerator, those both mean the same thing. So don't let the 4/5 and that fraction kind of freak you out. It's still just a constant, and we can use that constant rule. So we did a negative. We did one that had a fraction in the constant. Let's continue this and do one with a radical to make sure we're still good with that, and then we'll go into some other rules. So I want to find the derivative of this. Again, 2 is just that constant, so I'm going to leave it right there. But that's a radical, so I'm going to rewrite it. So that would be equal to 2x to the 1/2. All I did was apply my rules of algebra back from algebra 1. So whenever you have a radical, you want to change it into an exponent. And so just for our note's sake, let's write that down. Whenever you have a radical, change into an exponent. And so all we have done is change what that function looks like. So now I'm going to take the derivative. So f prime of x would be equal to 2 is going to stay out front, 1/2 is going to be brought down, and then I'm going to do 1/2 minus 1. So cleaning this up, these 2's would cancel. So we get x to the 1/2 minus 1. That's like a minus 2 over 2. So I have a negative 1/2. I told you, negatives and fractions are going to trip you up, and this has both in it. And so again, I can't leave a negative exponent. So I'm going to have to do a little bit more algebra. Even though I've found that derivative, I'm going to clean it up. So I'm going to put this over 1, and I'm going to move this to the bottom. So I get f prime of x equal to 1 over x to the 1/2. And then this was given to me in radical form, so this would be 1 over the square root of x. So make sure you always clean it up as much as possible. Stopping along the way before your cleanup, you're going to see -1, didn't simplify, etc. So we've got our constant rule, we've got our power rule, we've got it when we have a constant within there and using the power rule. The next one is going to be your sum and difference rules. And so sum and difference rules, this says if you're taking a derivative with respect to x of f of x plus or minus, doesn't matter whether you're adding or subtracting, g of x, then that will be equal to f prime of x plus or minus g prime of x. So basically, you're going to take the derivative of the individual parts and then just keep on adding and subtracting them as they were designed. And so now we can go away from these one-term derivatives that we've been doing this entire section and move into ones that have multiple terms, basically just taking the derivative of the terms as we go. And so here's some examples here, and let's work them out. So f of x is equal to x to the 3rd power minus 4x plus 5. And so f prime of x would be equal to, and you just take the derivative of the pieces as you go. So the derivative of x cubed would be 3x squared. Again, you're going to see me doing this a lot quicker. I'm not going to say, oh, and make my circles, bring them down, subtract 1. I'm just going to say 3x squared. The derivative of negative 4x would be negative 4. Remember, we talked about how in that previous one, it becomes a 0. That's just like a linear function. The slope of it's negative 4. And then plus 5, its derivative would just be 0. That's the very first thing we learned in this lecture. So really, at the end of the day, our answer would just be 3x squared minus 4. Let's do another one. Less talking, though. G of x is equal to negative 4x cubed over 2 plus 9x squared minus 2. So that means g prime of x would be equal to, bring the 3 down, and so that would be negative 4 over 2. So it would be times 3x squared. Bring the 2 out front here, so it would be plus 18x. And then negative 2, its derivative is just 0. So not necessarily to put 0, but I don't want you to think I left it out. Now I'm just going to clean it up. So let's see, negative 4 over 2, that's negative 2. Probably could have reduced before we started. And so that gives me negative 2 times 3, so negative 6x squared plus 18x. And then that would be my derivative of that function. Let's take a moment and kind of switch over to our trig functions. I know we've already kind of worked with our unit circled, and it was just a review in an earlier module in the course to remind you of your unit circle and sine and cosine, but we haven't really delved in. Here you're going to see a little bit more use with them. So we're going to begin with some basics, our 2 basic functions, and these are just going to be rules. These are just going to be facts or laws that we're going to know and use. They're not going to be one that we are deriving. And so 2 things that you need to remember. The derivative with respect to x of sine x is equal to cosine. The derivative with respect to x of cosine is equal to negative sine. And as we add more tools to our tool belt, we'll be able to do the other 4 trig functions as well. So you need to memorize those, commit them to your memory, because as you know in earlier exams, there will be no formulas or charts or anything given. You will have to know these 2 facts. So you can see that when you're taking the derivative of sine, it's cosine. Great. You see a relationship there. When you're taking the derivative of cosine, you're going to notice that it is negative sine. So that's probably the key takeaway, is remember which one has the negative on it. So if we look at these 2 examples, we're still going to use our other rules that we've seen, but now we're going to plug in these 2 trig rules. So first example says y is equal to 2 sine x. So when I come in here and I go to take the derivative, 2 is just going to stay where it is. The derivative of sine x is cosine x, and we're done. Next one says y is equal to sine x over 2. Well, this is the same as 1/2 sine x, and so that means when I come in here and I take y prime, that's going to be equal to 1/2. Sine x is just equal to cosine x, and so its derivative is just cosine x over 2, if I go back to that format that I originally started with. Let's do one with cosine. So y is equal to cosine x over 2. Again, I'm just going to rewrite that as y being equal to 1/2 cosine x. So that when I come over here and say y prime, 1/2 is going to go along for the ride. Now cosine is equal to negative sine, so I'm saying negative sine x. I'm going to stick that negative right there, because if I put it between the 1/2 and the sine, it might look like subtraction and mess me up. So that would be my answer. Y prime, I kind of messed it up, so I'm going to rewrite it, is negative 1/2 sine x, and I'm done. So sine and cosine are not too bad, but you do need to remember which one has the negative on it so you can figure that out from there. Now we've got our constant rules and our power rules. We've got sine, we've got cosine. There's got to be more than this than just taking functions, spitting out derivatives. Let's apply this a little bit and see how we can work this into some other situations. So let's look at this next page here. It says rates of change. We have learned that when we have rates of change, known as velocity, that's the change in distance over the change in time. Well, if we take that change in distance over the rate of time, we also call that slope. And if we're looking at the slope at an individual point, we call that a derivative. And so when I look at this next example, it says keywords are crucial here. Find the average rate of change. I'm finding the average. So if I'm looking at the average, find the average velocity. I was getting ahead of myself. So if I'm looking at the average velocity, that's going to have me result back to my algebra. M equal to y2 minus y1 over x2 minus x1. And so if I'm looking at the position function of a falling object, say s of t equal to negative 16t squared plus 100. So kind of interesting. The negative 16t squared is your accounting for gravity. Your t is your time in seconds, and s of t is your feet. So if I take this problem and I say, what is the average velocity over the interval from 1 to 2, and that's an interval, not an ordered pair, then I am just applying algebra. I want to find the average velocity over the interval from 1 to 2. So this would be my x1, this would be my x2, this would be my formula for average velocity. So it looks like I just need a y1 value and a y2 value. In order to find those, I'm just going to plug into my original function. So s of 1 would be equal to negative 16 times 1 squared plus 100. And s of 2 would be equal to negative 16, 2 squared plus 100. So grab your calculator, and when you compute this out, this gives me 84. So that would be my y1. And this would give me negative 16, 2 squared plus 100. So that would give me 36. And that would be my y2. Now I have enough information that I can do my slope formula. So I say average velocity or slope would be equal to, let's see, 36 minus 84 all over 2 minus 1. 36 minus 84 would give me negative 48 over 1. And this is feet per second because that was distance over time. And so that means, what is the average velocity between 1 and 2 seconds? That would be negative 48 feet per second. And so when you're doing average velocity, that's just going to be slope between 2 points. But let's look at this next one, and let's look at instantaneous velocity. And this instantaneous velocity, that's what we've been leading up to with all of our lectures at this point. I want the instantaneous velocity. When you see the word instantaneous, you need to be thinking derivative. And so here's my function here of s of t equal to negative 16t squared plus 100. So s of t would be equal to negative 32t plus 0. So I'm just going to say negative 32t, and that's my derivative. And so what would be the instantaneous velocity at, say, t equal to 1? Well, then that would be s prime of 1 equal to negative 32 times 1. So it would be negative 32 feet per second. What would it be at t equal to 2? And that would just be s prime of 2 equal to negative 32 times 2. So negative 64 feet per second. So it makes sense if I averaged between 1 and 2 seconds that I would be at negative 48 feet per second, the average between those two. So I just want to emphasize to you those keywords of average, meaning just your algebra pre-cal dates, instantaneous, that is your calculus, that's your slope. So as you could imagine, if I'm working with derivatives, I can repeat this process as much as my function allows. And so that's what we call a higher order derivative. And we're almost done here. A higher order derivative is just how many times we're going to keep taking the derivative of the result that we get. So some notation to help you with is if you just have y prime, that's your first derivative. Y double prime, that's your second derivative. So take your first derivative and find your second. Y with 3 marks is your third derivative, and then we get tired of making those marks, so we say y with a parentheses 4, and that's your fourth derivative. But you can see that if I move beyond my first derivative and I am anywhere within here, it is a stair step. I cannot jump to the fourth derivative without any work in between. I can't jump to the third derivative without finding the first or second. So it is a progression, and if you're ever asked for a derivative of second, third, fourth, etc., you will have to find all the derivatives in between. Now there is a little bit other notation. I mean, they can take all of our derivative notations that we saw earlier and change them up. So that would be f with 1 mark. This would be 2 marks. 3 marks, and then again we could put a 4 right there. And then you can take all your other notations as well and see those different markings. These are kind of your most two common ones. If you went to like dy dx, they do like a d squared y over dx squared, and they put that kind of squared in a different spot, etc., etc., so you don't think you're trying to square something algebraically and that it's your notation change. So let's move into our position function and talk about what those derivatives mean, and that's really where this has the application. Sorry, I lost my train of thought there. So s of t, remember that's like your y function or your f of x function. And so this is going to be, as you know, your position function. And so if I come to s prime of t, s prime of t, and we just saw this, is our velocity function. And so when we find the first derivative, we're able to locate our velocities. Your s double prime of t, this is the derivative of your velocity, or we call it our acceleration function. And so pretty neat that we can now take a position function that you saw in algebra and pre-cal days, take its derivative and find your velocities, take its derivative again and find your acceleration. So it really diversifies what we're able to do within the realms of these functions. So I hope this helped. I know these are getting a little bit longer, but please reach out if you need assistance as you're working through the homeworks.